The morning of January 16, 1945, somewhere over Japanese-held territory in China, First Lieutenant Oliver Strawbridge nursed his damaged P-51 Mustang toward what he hoped would be friendly territory. Enemy ground fire had found its mark during a low-level strafing run, and now his fighter, nicknamed Evalina after his girlfriend back home, was bleeding hydraulic fluid and losing altitude. The engine still ran, but the gauges told a story of declining pressure and rising temperatures. Ahead, through the haze, an airfield appeared. Strawbridge had no choice. He brought the Mustang down onto the runway at Sichuan Airfield, the landing gear holding as he rolled to a stop in enemy territory. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within minutes, Japanese ground crews swarmed the aircraft. They'd been waiting for something like this. For over a year, Japanese pilots had been sending back increasingly desperate reports about American fighters that seemed to defy the laws of physics. The P-51 Mustang had appeared over Burma in late 1943, and within months it had become a nightmare. Japanese pilots described speeds that their own fighters couldn't match, dive performance that made pursuit suicidal, and combat radius that meant nowhere was safe anymore. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But reports from traumatized pilots weren't engineering data. They couldn't explain how the Americans had built a fighter that could fly from China deep into Japanese-held territory and return home. They couldn't detail the manufacturing techniques that produced such performance. Here, sitting intact on a Japanese airfield, was the answer to every question that had been haunting the Imperial Japanese Army Air Force since the Mustang first appeared. This wasn't wreckage to be studied in fragments. This was a complete, operational American fighter that could be flown, tested, and analyzed. The Japanese had captured technological intelligence that might be their last chance to develop effective countermeasures against American air superiority. What they would discover in the weeks ahead would shake the foundations of Japanese aviation doctrine and reveal a gap between Japanese and American engineering that no amount of pilot skill or tactical brilliance could overcome. The story of Evalina's capture and evaluation represents one of the most revealing moments of the Pacific Air War, when Japan's best engineers confronted the full reality of what they were fighting against. By early 1945, Japanese aviation was dying. Not slowly, not gradually, but hemorrhaging pilots and aircraft at rates that made strategic victory impossible. The situation had become so desperate that honest assessment risked being labeled defeatism. The Mitsubishi A6M0, which had terrorized Allied pilots from Pearl Harbor through 1942, was now a death trap. American pilots had learned its weaknesses through hard experience and captured examples: poor, high-speed handling, virtually no armor protection, wing structures that failed under heavy G-loads during high-speed maneuvers. But more importantly, the Americans had built fighters specifically designed to exploit those weaknesses. The P-51 Mustang represented the apex of that evolution. Intelligence reports filtering back to Tokyo described an aircraft that could absorb extraordinary damage and keep flying. Pilots reported fighters that could dive away from a zero at speeds that made pursuit not just futile but suicidal. They described firepower that could shred a Japanese fighter with a single burst. 6 50-caliber machine guns, each loaded with hundreds of rounds of armor-piercing incendiary ammunition. The psychological impact was devastating. Japanese pilots who'd spent years mastering their craft now watched American fighters escape impossible situations simply by diving away and using superior speed. But the most troubling reports concerned range. By late 1944, P-51 seconds were appearing over targets that should have been beyond any fighter's operational radius. Japanese commanders understood the implication. If the Americans captured islands close enough to Japan, these Mustangs could escort heavy bombers all the way to the homeland. The strategic calculus was brutal. Japan's industry couldn't replace losses at American production rates. Training programs couldn't produce pilots fast enough to offset casualties. Every engagement left Japan proportionally weaker, even when Japanese forces inflicted significant American casualties. The intelligence gap facing Japanese aviation was crushing. American aircraft were evolving rapidly, with new models and variants appearing regularly, each incorporating lessons from combat and advances in technology. Japanese intelligence could sometimes obtain general specifications through various channels, but they couldn't explain the practical engineering solutions that made those specifications possible. How did American engines produce such enormous power while remaining reliable enough for sustained operations? How did their aircraft survive damage that would obliterate a Japanese fighter? What materials and manufacturing techniques enabled them to build such robust structures without unacceptable weight penalties? The questions multiplied faster than answers appeared. Japanese engineers had theories, of course. Reports from combat pilots provided clues. Captured wreckage offered fragments of understanding, but wreckage was incomplete, damaged, often burned. You couldn't test performance from scattered pieces. You couldn't run an engine that had been smashed on impact. You couldn't evaluate handling characteristics from a crumpled airframe. What Japanese aviation desperately needed was a complete, intact, operational example of America's most dangerous fighter. On January 16th, 1945, that's exactly what they got. The capture of Evalina represented something beyond mere technical intelligence. It represented a chance to understand the philosophy behind American fighter design. Japanese aviation had been built on specific assumptions about what made an effective fighter, maneuverability and range above all else. Skilled pilots who didn't need heavy armor or excessive firepower. Elegance in design reflecting superiority in combat. The Zero had embodied that philosophy perfectly, and for a brief window, it had dominated Pacific skies. But now Japanese pilots were dying in droves, and the aircraft killing them represented completely opposite priorities. Heavy armor, overwhelming firepower, robust construction, enormous power, everything Japanese doctrine had dismissed as unnecessary weight was proving decisive in combat. Examining the Mustang meant confronting the possibility that Japan's fundamental assumptions about fighter design had been catastrophically wrong, that their elegant, maneuverable fighters weren't losing because of pilot quality or tactical errors, but because the underlying engineering philosophy was obsolete. There was also desperate urgency. By January 1945, the strategic situation was deteriorating rapidly. American forces were advancing across the Pacific, capturing islands that would bring the Japanese homeland within range of American heavy bombers. The Philippines were falling. Iwo Jima would be next, putting American fighters within 750 miles of Tokyo. If Japanese engineers could identify some exploitable weakness in the Mustang's design, some tactical vulnerability that skilled pilots could leverage, it might buy time. It might make the American advance more costly. It might create negotiating leverage. But if the Mustang proved as superior as combat reports suggested, then Japan faced a technological gap that couldn't be closed with available resources. Either outcome would shape strategic planning for the war's final phase. The stakes couldn't have been higher. The captured aircraft arrived at the Japanese Army Air Inspection Center at Fusa in pieces, partially disassembled for transport, but with most major components intact. The recovery team had done remarkable work under difficult circumstances, managing to preserve the aircraft's essential systems despite capturing it in a combat zone. Japanese engineers immediately established systematic documentation procedures, photographing every component before detailed examination began. They knew this might be their only chance to study an intact example of America's most successful long-range fighter. The initial walk-around inspection took days. Teams of specialists examined different aspects simultaneously. Structures engineers focused on the airframe, looking for design innovations or construction techniques. Power plant specialists studied the massive Packard Merlin engine, noting every detail of its installation and cooling systems. Armament experts documented the gun installation, ammunition, storage, and fire control systems. Avionics technicians examined the radio equipment, instrumentation, and electrical systems. Everything was measured, photographed, documented. What emerged from those initial examinations was an aircraft that looked brutish compared to the elegant lines of Japanese fighters. The P-51C was heavier, thicker, more substantial in every dimension. Where Japanese fighters pursued grace through weight reduction, this American machine seemed to embrace mass. The engineers walked around Evalina slowly that first day, taking measurements, running their hands over riveted panels, examining the broad wings and the distinctive ventral scoop that housed the radiator. They noted armor plate behind the pilot's seat, thick enough to stop rifle-caliber rounds and even some cannon shells. They observed robust landing gear, built to handle the brutal stress of operations from rough forward airstrips. They examined the 650 caliber machine guns, 3 in each wing, with ammunition boxes holding hundreds of rounds. The ammunition feed systems were sophisticated, designed for reliability under high G-loads and extreme temperatures. Everything about the Mustang spoke to a design philosophy that prioritized pilot survival, sustained firepower, and rugged reliability over the pure performance metrics that had guided Japanese fighter development. This wasn't just a different aircraft. It was a different answer to the fundamental question of what made an effective fighter. The Japanese engineers understood they were looking at more than enemy technology. They were confronting an entirely different industrial philosophy, one that might explain why Japan was losing the air war. The P-51 Mustang wasn't designed to be the prettiest fighter in the sky. It was designed around a specific engine and a specific mission requirement, and every compromise reflected those priorities. The heart of the aircraft was the Packard V1650 Merlin, a license-built version of the British Rolls-Royce Merlin 61 engine. This power plant represented one of the most significant engineering achievements of the war. A liquid-cooled 12-cylinder V-configuration engine with a 2-stage, 2-speed supercharger that allowed it to maintain power at altitudes where most engines gasped for oxygen. The Merlin in Evalina produced approximately 1,695 horsepower at takeoff, and critically, it maintained over 1,400 horsepower at altitudes above 20,000 feet. Japanese engineers examining the engine were immediately struck by its size and complexity. The Nakajima Ki 84 Frank, Japan's best fighter, used the Nakajima Ha-45 radial engine, producing roughly 1,900 horsepower at takeoff. But that power fell off dramatically at altitude, and the engine required constant maintenance to remain operational. The Merlin, by contrast, seemed almost over-engineered. Heavy, yes, but designed for sustained operations under combat conditions. The supercharger system particularly impressed Japanese engineers. Japanese fighters used mechanically driven superchargers, simpler systems that were lighter but less efficient at high altitude. The Merlin's 2-stage system used one supercharger to feed compressed air into a second supercharger, with an intercooler between stages to reduce air temperature and increase density. This allowed the engine to maintain power at altitudes where Japanese fighters struggled. At 30,000 feet, a P-51 could still produce maximum horsepower, while a Ki 84 was losing power rapidly. Weight was another revelation. The P-51C weighed approximately 7,125 pounds empty. Fully loaded with fuel, ammunition, and pilot, it could reach 10,000 pounds. The Ki 84, by comparison, weighed roughly 5,864 pounds empty. Japanese design philosophy emphasized minimum weight for maximum maneuverability. The Americans had apparently decided that survivability justified extra weight, and the Mustang's performance proved they were right. Despite being heavier, the P-51 was faster. Maximum speed was approximately 437 miles per hour at 25,000 feet. The Ki 84, when properly maintained and using good fuel, could reach perhaps 427 miles per hour. But that specification represented optimal conditions with fresh engines and high-octane fuel, conditions that became increasingly rare as the war progressed. The Mustang's speed advantage came partly from aerodynamics. North American Aviation had employed NACA laminar flow wing technology, a revolutionary airfoil design that maintained smooth airflow over a greater percentage of the wing's surface. Traditional wings generated turbulent airflow relatively quickly, increasing drag. The laminar flow wing delayed that transition, keeping airflow smooth and reducing drag significantly. Japanese engineers examining Evalina's wings could see the design was different, but understanding how to replicate it was another matter entirely. The cooling system represented another area where American engineering had solved problems Japanese designers still struggled with. Liquid-cooled engines generated enormous heat that had to be dissipated efficiently without creating excessive drag. The Mustang's solution was elegant. The radiator was mounted in a ventral scoop beneath the fuselage, positioned to use the Meredith effect. As air flowed through the radiator, it heated up and expanded, creating thrust that partially offset the drag of the scoop itself. Japanese engineers had heard of this principle but hadn't successfully implemented it. Their liquid-cooled fighters used radiators that created significant drag without offsetting thrust benefits. Then there was range. The P-51C carried 170 gallons of internal fuel, giving it a combat radius of roughly 475 miles on internal fuel alone. But the Mustang could carry external drop tanks, typically two 110-gallon tanks under the wings. With external tanks, the combat radius extended to over 750 miles. This meant a Mustang taking off from Iwo Jima could fly to Tokyo, engage in combat, and return home. No Japanese fighter could match that range while maintaining combat capability. Japanese fighters achieved long range through different methods. The Zero carried substantial internal fuel but did so at the cost of armor, self-sealing tanks, and structural strength. When damaged, Zeros burned easily. The fuel system had no redundancy. The Mustang's fuel tanks incorporated multiple layers of rubber that would swell when exposed to fuel, automatically sealing bullet holes. The system wasn't perfect, but it meant a Mustang could take hits to the fuel system and keep flying. A Zero with similar damage would likely burn. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese test pilot Major Yasuhiko Kuroe, a 30-victory ace, flew Evalina from China back to Fusa. His first impressions were recorded in post-war interviews. The cockpit was spacious, far more comfortable than Japanese fighters. The seat was surrounded by armor plate, something he'd never seen in a fighter before. The bulletproof glass was thicker and clearer than Japanese equivalents. There was an automatic radiator shutter, an oxygen system more sophisticated than anything Japan produced, and instrumentation that seemed almost luxurious compared to the minimal gauges in Japanese fighters. Starting the engine revealed another difference. The Merlin fired up smoothly, settled into a steady idle, and ran without the excessive vibration that plagued Japanese radial engines. When Kuroe advanced the throttle for takeoff, the acceleration was immediate and smooth. The Mustang lifted off easily, climbed steadily, and responded crisply to control inputs. Kuroe later recalled being astonished by the aircraft's handling. Turn characteristics were excellent, almost matching the key 84 inches horizontal turns. The Mustang couldn't outturn a Zero in a slow-speed turning fight, but at speeds above 300 miles per hour, it could turn with any Japanese fighter while maintaining energy better. Dive performance was particularly impressive. Japanese pilots had reported that P-51 seconds could simply dive away from pursuit, and now Kuroe understood why. The Mustang remained controllable and stable at speeds that would have caused Japanese fighters to buffet violently or suffer structural failure. The airframe was simply stronger, built to higher load factors than Japanese designs. In a dive, the Mustang accelerated rapidly and could reach speeds approaching 500 miles per hour without breaking apart. Japanese fighters couldn't follow without risking structural failure. The radio equipment impressed everyone who examined it. American radios were reliable, clear, and had significantly better range than Japanese equivalents. More importantly, every Mustang had a working radio. Japanese fighters often had radios installed, but the equipment was so unreliable that many pilots simply removed them to save weight. Communication in Japanese formations relied heavily on visual signals. American pilots could coordinate complex tactics via radio, calling out threats, directing attacks, and maintaining formation cohesion even in chaotic combat. The tactical advantage was enormous. One detail that surprised Japanese ground crews was the absence of oil leaks. Every Japanese engine leaked oil to some extent. Mechanics considered it normal, inevitable. The Merlin didn't leak. The installation was tight, the gaskets effective, the systems properly sealed. It seemed like a small thing, but it spoke to manufacturing quality control and engineering precision that Japanese industry was struggling to maintain. As the war progressed and skilled workers were drafted or killed, Japanese manufacturing quality had deteriorated. The Mustang represented what American industry could produce when quality control remained high. Evalina was transferred to the Aquino Flying Training Division for further evaluation and mock combat against Japanese fighters, including the P-43 Oscar, P-61 Tony, and P-84 Frank. These comparative trials revealed uncomfortable truths. Against the P-43, the Mustang was faster, more heavily armed, better protected, and had vastly superior range. The Oscar could outturn the Mustang in slow-speed maneuvering, but that advantage was irrelevant if the American pilot refused to engage in turning fights. Against the P-61, another liquid-cooled fighter, the Mustang showed superior performance at all altitudes and better reliability. The Tony's Kawasaki Ha-40 engine was temperamental and underpowered compared to the Merlin. Against the Ki-84, the comparison was closest. Both aircraft had similar top speeds under optimal conditions, similar firepower, and comparable handling. But the Mustang had better range, better reliability, superior high-altitude performance, and more robust construction. In mock combat, experienced pilots could exploit the Frank's slightly better maneuverability at medium altitudes, but the Mustang's advantages in speed and structural strength meant American pilots could dictate engagement terms. They could choose when to fight and when to disengage. Major Kuroe, who flew both the Ki-84 and the captured Mustang extensively, later stated he had such confidence in the P-51 that he feared no Japanese fighter. This, from an experienced combat pilot who knew both aircraft intimately. The evaluation also included another remarkable pilot, First Lieutenant Yohei Hinoki, one of the first Japanese pilots to shoot down a Mustang back in November 1943. Days after that victory, Hinoki had himself been shot down by a Mustang and lost a leg. He returned to combat with an artificial leg and was selected to evaluate Evalina specifically because of his combat experience against the type. Hinoki's impressions were recorded in detail. He found the cockpit spacious enough that his artificial leg didn't interfere with rudder control. He was impressed by the thick armor surrounding the seat, armor that would have prevented his own injury. The bulletproof glass was superior to Japanese equivalents. The overall equipment level was better than any Japanese fighter he'd flown. Most significantly, Hinoki noted the absence of any major flaws. The Mustang wasn't exceptional in one area at the cost of critical weaknesses elsewhere. It was simply well executed in every aspect. In mid-April 1945, Kuroe was placed in charge of a flying circus composed of captured Allied aircraft. This group toured Japanese fighter units to train pilots on how to fight American aircraft. Evalina was the star attraction. Pilots would fly mock combat against the Mustang, learning firsthand what they faced. One pilot, First Lieutenant Masatsugu Sumita from the 18th Sentai, recalled learning how to break out of the P-51's axis when being pursued. These demonstrations provided valuable tactical training, but they also revealed the fundamental challenge. Even knowing the Mustang's characteristics, defeating it required executing perfect tactics under combat stress, while the American pilot made mistakes. The psychological impact of these evaluations cannot be overstated. Japanese pilots had been fighting P-51 seconds for over a year, watching their comrades die, absorbing losses they couldn't replace. Now their own test pilots and engineers were confirming what combat experience had already taught. The Mustang wasn't just better in one or two areas, it was comprehensively superior across almost every metric that mattered in combat. Speed, range, firepower, protection, reliability, manufacturing quality. The only area where Japanese fighters maintained advantage was low-speed maneuverability, and American tactics simply avoided fights where that mattered. Senior officers reviewing the evaluation reports faced uncomfortable questions. If American engineering and manufacturing had produced such comprehensively superior fighters, what did that imply about Japan's ability to compete industrially? If skilled test pilots flying optimal examples of Japan's best fighters couldn't identify exploitable weaknesses in the Mustang, What chance did average pilots in poorly maintained aircraft have? The answers suggested outcomes that contradicted official optimism about Japan's strategic position. Evalina's evaluation occurred against a backdrop of deteriorating strategic circumstances. In March 1945, American forces captured Iwo Jima after brutal fighting that cost thousands of lives on both sides. Almost immediately, American engineers began extending the island's airfields to accommodate heavy bombers and their fighter escorts. Within weeks, P-51Ds, even newer models than Evalina, began arriving. By April, Mustangs based on Iwo were escorting B-29 raids over Japan itself, exactly as Japanese analysis had predicted. The appearance of American fighters over the homeland was psychologically devastating for Japanese civilians and military personnel who'd been assured that Japan's defenses remained strong. But for Japanese pilots scrambling to intercept bomber formations, the presence of Mustang escorts was worse than demoralizing. It was lethal. American fighters now operated over Japan with impunity, shooting down Japanese interceptors, strafing airfields, destroying aircraft on the ground. Every sortie reduced Japan's already depleted fighter strength. The technical reports compiled from Evalina's evaluation made their way to senior officers and strategic planners throughout the Japanese military establishment. What they read confirmed the worst assessments of Japan's situation. The Mustang represented not just superior individual aircraft design, but superiority in every aspect of aviation development: materials science, manufacturing precision, quality control, pilot protection, systems integration, logistical support. The gap wasn't something that could be closed with better tactics or improved pilot training. It was fundamental, rooted in industrial capacity and engineering philosophy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Japanese engineers had done everything right in their evaluation. They'd been thorough, professional, and brutally honest in their assessments. But honesty only mattered if you could act on what you learned. By spring 1945, Japan couldn't act on the lessons Evalina taught. The material shortages, industrial bottlenecks, and resource constraints that made Japan unable to match American fighter performance weren't going to be solved by better engineering. They were fundamental limitations of Japan's industrial economy, and no amount of captured enemy equipment could change that reality. Consider the numbers. North American aviation produced over 15,000 Mustangs between 1940 and 1945. Just one American manufacturer, producing one fighter type, built more aircraft than Japan's entire fighter production across all types during the same period. And that was just Mustangs. American factories were simultaneously producing Thunderbolts, Lightnings, Corsairs, Hellcats, and numerous other types. The industrial disparity was so vast that even if Japanese fighters had been qualitatively equal to American aircraft, Japan would still have been overwhelmed by sheer numbers. But the fighters weren't equal. Japanese engineers examining Evalina documented specific examples of American manufacturing superiority. The aluminum alloys used in the Mustang's structure were stronger and more consistent than Japanese equivalents. The steel in landing gear components was properly heat-treated, something Japanese manufacturing increasingly struggled to accomplish as skilled metallurgists became scarce. The engine showed precision machining that Japanese factories couldn't consistently replicate. Even seemingly minor details like wiring harnesses and electrical connectors reflected higher manufacturing standards. The fuel situation compounded every other problem. The Mustang's Merlin engine was designed to run on 100-octane aviation gasoline. Japanese fighters used lower-octane fuel, typically 92-octane or even lower as the war progressed. When American forces captured Key 84, Franks, after the war, using 100-octane fuel, reliability problems that plagued the type largely disappeared. The Homer engine's reputation for unreliability wasn't entirely a design flaw. It was partly the result of running an advanced, high-compression engine on fuel with insufficient octane rating. Detonation and knock-damaged engines required more frequent maintenance and reduced performance. Japan's fuel crisis was itself a symptom of larger strategic failures. American submarines had strangled Japanese oil imports from the Dutch East Indies. Without adequate petroleum supplies, Japan couldn't produce high-octane aviation fuel in quantities needed. This meant even well-designed Japanese fighters operated at reduced performance because the fuel they ran on couldn't support their engines' designed output. The Americans faced no such constraints. Their fuel supplies were effectively unlimited, and refineries could produce high-octane fuel in whatever quantities the military required. The range equation revealed similar strategic implications. The Mustang could fly from Iwo Jima to Tokyo and back, a round trip of 1,500 miles with combat reserves. This capability stemmed from multiple factors. Efficient aerodynamics reduced fuel consumption, large internal fuel capacity provided baseline range, external drop tanks extended range further. But critically, American logistics meant that every forward base had adequate fuel supplies. Japanese forces by 1945 often lacked fuel to fully tank their fighters, even when aircraft were available. Pilots sometimes flew missions with partial fuel loads simply because the base didn't have enough gasoline. American pilots also had sophisticated navigation equipment and reliable radios that made long over-water flights less dangerous. The P-51's radio direction finder could home on radio beacons, helping pilots navigate in poor visibility or return to base when disoriented. Japanese fighters had rudimentary navigation equipment that forced pilots to rely on visual navigation and dead reckoning. In the Pacific Theater, where fog, clouds, and vast expanses of water were constant factors, navigation equipment wasn't a luxury. It was the difference between completing a mission and disappearing over empty ocean. The armament comparison was equally discouraging. The Mustang's 650 caliber machine guns fired approximately 1,800 rounds combined in the P-51C variant. The weapons were reliable, the ammunition supply was consistent, and the ballistics were well understood. Japanese 20mm cannons hit harder per round, but Japanese pilots frequently reported ammunition malfunctions, particularly with armor-piercing rounds. Quality control in ammunition manufacturing had deteriorated along with everything else in Japanese industry. Pilots sometimes found that significant percentages of their ammunition were duds. American ammunition, manufactured under strict quality control, with consistent propellants and primers, functioned reliably. The self-sealing fuel tanks represented another area where American engineering had solved problems Japanese designers hadn't prioritized until too late. When bullets punctured the Mustang's fuel tanks, the multiple layers of rubber lining would swell on contact with gasoline, sealing holes automatically. The system worked for small arms fire and even some cannon fragments. It didn't make the aircraft invulnerable, but it significantly improved survivability. Japanese fighters that added self-sealing tanks later in the war found the systems added weight and complexity while reducing fuel capacity. The Americans had designed them in from the beginning, accepting the compromises as worthwhile for pilot survival. Pilot protection revealed philosophical differences that had life-or-death consequences. The armor plate behind the Mustang's pilot seat weighed approximately 22 pounds. The bulletproof windscreen added more weight. Engine protection added still more. Japanese designers had historically rejected such features as unnecessary weight that reduced performance and maneuverability. The assumption was that skilled pilots wouldn't get hit, and if they did, it was their fault for poor situational awareness. The Americans assumed pilots would get hit regardless of skill, because combat was chaotic and random. Bringing pilots home meant they could fight again tomorrow. The statistical evidence supported the American approach. American pilot casualty rates in the Pacific Theater, while certainly significant in absolute terms, were substantially lower than Japanese rates when adjusted for number of sorties and intensity of combat. Part of this disparity came from numerical superiority and better training, but a significant portion came from simple survivability. American pilots walked away from battle damage and crashes that would have killed Japanese pilots. The Mustang could absorb punishment that would destroy a Zero or a Frank. Pilot armor stopped bullets that would have been fatal. Self-sealing tanks prevented fires that would have incinerated the pilot. Structural strength allowed the aircraft to survive crash landings where lighter fighters would disintegrate. The cumulative effect of these differences was that American fighter groups maintained strength while Japanese units bled away. An American squadron might lose 3 aircraft in combat, but have all 3 pilots rescued by submarines or flying boats positioned for search and rescue. Those pilots returned to duty with combat experience intact. A Japanese unit losing 3 aircraft typically lost 3 irreplaceable trained pilots. Even when Japanese pilots survived shootdowns, they often ended up in the ocean with no rescue capability. The attrition was unsustainable. By the time Evalina's evaluation was complete, Japanese strategic planners were working with brutal arithmetic. The captured Mustang had helped them understand exactly why they were losing the air war. But understanding the problem didn't provide solutions. Some officials advocated for immediate negotiated peace before Japan's situation became completely hopeless. Others pushed for a final, decisive battle, one massive engagement that would inflict such catastrophic losses on American forces that negotiations might become possible. These debates occurred against the backdrop of the Mustang analysis sitting on desks in Tokyo, a physical reminder that Japan was fighting an enemy whose industrial capacity made conventional military victory impossible. The captured Hellcat evaluation that had preceded Evalina's analysis by several months had revealed similar disparities in naval aviation. Now, the Mustang evaluation confirmed the same pattern in land-based fighters. American aircraft weren't just marginally better, they were comprehensively superior across almost every metric, and that superiority stemmed from industrial advantages Japan couldn't overcome. The honest assessments from experienced test pilots made any claims about superior Japanese fighting spirit seem hollow. Spirit didn't matter when the enemy's aircraft could fly faster, farther, and survive damage that destroyed your own fighters. Evalina was eventually grounded by a burned-out generator. Japanese engineers lacked spare parts to repair it. In a darkly ironic twist, one Japanese ace was tasked with shooting down another P-51, specifically to obtain replacement parts. He succeeded in downing a Mustang, but the aircraft crashed into the ocean, making it unsalvageable. The captured fighter that had revealed so much about American aviation superiority ended its service life because Japan's logistics system couldn't provide a single replacement generator. That failure encapsulated Japan's entire strategic situation. Understanding American technology meant nothing without the industrial capacity to respond effectively. 2 additional P-51Ds were reportedly captured in mainland Japan in 1945, but their fates are unknown. They likely suffered the same end as most Japanese equipment in the war's final months, destroyed by bombing or deliberately demolished by retreating forces. The technical reports from Evalina's evaluation survived in Japanese archives, testament to professional engineering work carried out under desperate circumstances. After the war, American intelligence officers found these reports when they occupied Yokosuka and other Japanese aviation facilities. The documents were remarkably thorough, showing understanding of the Mustang's design that rivaled North American aviation's own engineering documentation. The legacy of Evalina's capture and evaluation extends beyond its immediate strategic impact. It represents a case study in how wars are won and lost at the intersection of design, philosophy, industrial capacity, and strategic vision. The Mustang succeeded not because it was the most elegant fighter, or the most maneuverable, or the fastest in all conditions. It succeeded because North American aviation and the United States Army Air Forces understood that winning an air war required aircraft that could be built in quantity, that could protect their pilots, that could absorb punishment and keep fighting, and that could be maintained under combat conditions by mechanics who weren't specialized craftsmen. The Japanese engineers who examined Evalina recognized superior engineering when they saw it. Their evaluations were honest, professional, and accurate. But recognition alone couldn't bridge the gap between understanding and implementation. The Zero had been designed for a short, decisive war where Japan's limited industrial capacity could produce enough fighters to achieve air superiority during a brief window. The Mustang was designed for a long attritional struggle where industrial might and pilot survivability would ultimately determine the victor. Both aircraft served their nation's strategic visions perfectly. The tragedy for Japan was that their strategic vision had been wrong from the beginning. There is a broader lesson about how technological competition works in wartime. The capture and analysis of enemy equipment is standard intelligence practice, pursued by all nations in all wars. Japan's engineers did everything right in evaluating Evalina. They were thorough, objective, and unflinchingly honest in their assessments. But intelligence only matters if you can act on it. By 1945, Japan couldn't act on what the Mustang revealed. The material shortages, industrial bottlenecks, and resource constraints weren't going to be solved by better information or improved engineering. They were fundamental limitations that no amount of captured enemy equipment could overcome. The Mustang's performance specifications told only part of the story. Maximum speed of 437 miles per hour was impressive, but it was the consistency of that performance that mattered strategically. American P-51 seconds could achieve their rated speed reliably because they had good fuel, proper maintenance, and consistent manufacturing quality. Japanese fighters often fell short of their theoretical specifications because fuel quality was poor, maintenance was inadequate, and manufacturing quality had deteriorated. Paper specifications became meaningless when real-world conditions prevented aircraft from achieving their design performance. Post-war testing of captured Japanese aircraft by American forces revealed that properly maintained examples with good fuel could perform significantly better than the war-weary fighters that American pilots actually encountered. The Key 84 Frank, when tested with high-octane American fuel and proper maintenance, achieved speeds approaching 427 miles per hour and showed excellent handling characteristics. But those test conditions didn't reflect the reality of Japanese operations in 1945, where fuel was scarce, maintenance was rushed, and manufacturing quality was inconsistent. The Mustang's advantage wasn't just that it was well designed. It was that American logistics and industrial systems ensured the design's potential was consistently realized in operational aircraft. The human cost embedded in these engineering and industrial differences was staggering. Japanese pilots in the war's final year were flying obsolete or poorly maintained fighters with inadequate training, facing American pilots in superior aircraft who had extensive training and combat experience. The outcome was predictable. Japanese aviation losses in 1945 were catastrophic, measured not just in destroyed aircraft, but in irreplaceable trained pilots. Young Japanese aviators were being sent into combat with perhaps 50 hours of flight training, facing American pilots who had 300 hours or more before seeing combat. Equipment disparities compounded skill disparities, creating a situation where Japanese pilots were being systematically slaughtered. The Mustangs that flew from Iwo Jima in the war's final months operated with near impunity over Japan. They escorted B-29 bombers that burned Japanese cities to ash. They strafed airfields, destroying aircraft on the ground. They shot down Japanese interceptors attempting to defend the homeland. The fighter pilots of the 7th Fighter Command, flying from Iwo, claimed 206 aerial victories between April and August 1945, representing 75% of all Pacific P-51 kills. The 15th Fighter Group led with 111 kills. The 21st Fighter Group tallied 71, and the 506th Fighter Group claimed 24. These numbers represented not just destroyed aircraft, but dead or wounded Japanese pilots that Japan couldn't replace. By summer 1945, the strategic calculus was brutally simple. Japan had perhaps 5,000 aircraft of all types remaining, most obsolete, many grounded for lack of fuel or spare parts. American forces approaching Okinawa and preparing for potential invasion of the home islands could call on thousands of carrier aircraft plus land-based air power from captured island bases. The ratio wasn't just unfavorable, it was apocalyptic. Understanding why you're losing doesn't matter much when the war is already lost. The final irony of Evalina's story is that the lessons learned were universal, but only one side could apply them. American aircraft designers took the P-51's combat record and refined its philosophy further. The Republic F-84 Thunderjet, developed in the late 1940s, inherited the Mustang's design DNA: heavy, fast, built to absorb punishment. The philosophy extended beyond fighters into attack aircraft. The A-10 Thunderbolt, II, introduced in the 1970s and still flying today, represents the P-51 concept taken to its logical extreme. Redundant flight controls, armored cockpit, self-sealing fuel tanks, engines positioned to shield each other from ground fire, and the ability to fly home with extensive battle damage. That aircraft exists because the Mustang proved the concept worked. Soviet aircraft designers studied captured German intelligence reports on Allied aircraft, including material from Japan. Post-war Soviet fighters showed increasing emphasis on pilot protection and system redundancy. The philosophy appeared in aircraft like the Sukhoi Su-25, the Soviet equivalent to the A-10, which incorporated many of the same survivability features. The Cold War's proxy conflicts in Korea, Vietnam, and Afghanistan provided endless validation that aircraft designed to bring pilots home were worth their weight penalties. Even the Germans learned the lesson, though they learned it too late to matter. Late-war German designs showed increased attention to pilot protection and fuel system survivability. Jet aircraft programs incorporated self-sealing tanks and better armor as standard equipment rather than afterthoughts. But by the time these improvements reached operational aircraft, Germany lacked the fuel, trained pilots, and industrial capacity to make any difference. The Luftwaffe, that had pioneered modern air combat tactics, found itself overwhelmed by opponents who'd mastered both tactics and industrial production. The captured P-51C, called Evalina, likely didn't survive the war. Records are incomplete, but most captured aircraft at Japanese facilities were either destroyed during Allied bombing raids or deliberately demolished by Japanese forces to prevent recapture. The aircraft that had revealed so much about American aviation superiority probably ended as twisted wreckage or was bulldozed into a disposal pit. But the aircraft's influence survived in the minds of every engineer and pilot who studied it. They'd witnessed proof that a fighter could be designed to survive punishment, maintain performance across all altitudes, operate at extended range, and protect its pilot, all while remaining manufacturable in large quantities. That proof changed how everyone thought about building fighters. Today, military aircraft survivability is a primary design consideration from the earliest conceptual stages, not an afterthought. Stealth technology, electronic countermeasures, and advanced materials have changed the specific methods, but the underlying philosophy remains unchanged. The best aircraft is the one that brings its pilot home. Modern fighters incorporate redundant flight controls, hardened fuel systems, armored cockpits, and systems designed to function even with battle damage. These features trace their philosophical roots directly to the design decisions made when North American aviation created the Mustang. The commercial aviation industry absorbed similar lessons. Modern airliners' obsession with redundancy, with multiple backup systems for every critical function, reflects the same engineering mindset that produced the P-51. The Boeing 747's four engines, the triple redundant hydraulic systems in modern airliners, the elaborate fire suppression systems, all embody the principle that bringing people home safely justifies extra weight, complexity, and cost. The lessons learned in combat aviation became doctrine in civilian aviation. Japanese aviation learned from the Mustang too, though the learning came too late to affect the war. Post-war Japanese aircraft design emphasized many of the qualities that Evalina's evaluation had revealed: quality manufacturing, reliable systems, comprehensive pilot protection, robust structures. The Japan Self-Defense Force operates fighters today that reflect hard lessons learned when Japanese test pilots flew a captured American fighter and realized how comprehensively they'd been outclassed. Those lessons were purchased with the lives of thousands of Japanese pilots who died flying fighters designed to outdated doctrine. The story of Evalina represents a moment when technological reality collided with strategic assumptions. Japanese aviation had been built on beliefs about what made an effective fighter: maneuverability, range achieved through lightweight, pilot skill over protection, elegance over brute force. Those beliefs had produced the Zero, which had dominated briefly before American fighters designed to opposite principles destroyed Japanese aviation. The captured Mustang forced Japanese engineers to confront the possibility that their fundamental assumptions were wrong. Not slightly wrong, not wrong in emphasis, but catastrophically wrong in conception. That recognition came too late for strategic adjustment. By January 1945, when Evalina landed at Sichuan airfield, Japan's strategic position was already hopeless. No fighter design, no matter how advanced, could overcome the industrial disparity or replace the pilots already lost. The Mustang evaluation confirmed what combat experience had already demonstrated. American aviation had achieved comprehensive superiority through better engineering, superior manufacturing, and industrial capacity that Japan couldn't match, understanding that reality didn't provide solutions. Sometimes, understanding the problem is the cruelest knowledge of all, because it forces you to watch defeat approaching with perfect clarity and no ability to prevent it. First Lieutenant Oliver Strawbridge, whose forced landing had provided Japan with such valuable intelligence, survived the war. He was captured and held as a prisoner until Japan's surrender in August 1945. He returned home to find that his personal aircraft, the fighter he'd named after his girlfriend, had become the subject of intensive analysis by enemy engineers who'd recognized its significance. His forced landing at Sichuan had unintentionally provided Japan with its most complete look at American fighter technology. But that intelligence, thorough as it was, hadn't changed the war's trajectory. Evalina had taught Japanese engineers exactly why they were losing. That knowledge just made the defeat more comprehensible, not more avoidable. The technical reports compiled from Evalina's evaluation remain in archives today. Hundreds of pages of careful analysis, professional engineering assessment, and increasingly desperate recommendations. They tell the story of an enemy who understood exactly why they were losing but lacked the means to change the outcome. In war, sometimes understanding the problem is the cruelest knowledge of all. That captured Mustang at Fusa taught Japan that lesson more thoroughly than any battle ever could. The fighter that Japanese pilots called unbeatable in combat proved equally unbeatable in analysis, not because it was perfect, but because it was professionally executed across every aspect that mattered, backed by industrial systems that ensured consistent performance, and employed by a military that understood how to leverage technological advantages into strategic victory. The P-51 Mustang sitting in that Japanese test facility, absorbing scrutiny from engineers who recognized quality even in an enemy's equipment, represented more than one aircraft. It represented the answer to Japan's strategic question about how to compete with American air power. The answer was that you couldn't, not with existing resources, not with current industrial capacity, not within remaining time. Sometimes intelligence gathering provides answers you didn't want to discover. Sometimes the most thorough analysis merely confirms your worst fears. And sometimes a captured aircraft tells you everything you need to know about why you're losing a war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.